is I'll record that at this video there will have 2 parts. Just got to make sure, you know, you get involved in these PowerPoints there and was I recording or not? I was recording. I'm recording still. So the whole idea here, this is how an ionic bond works. Ion, an atom with a charge. 1 electron or 2, sometimes 3 electrons will jump, okay, and you will create a positive atom, a positive ion, and a negative ion, and there will be a bond there. All right, that's what we call an ionic bond. All right, creates ions. Covalent bonds. Here we're talking about, you going back into here, you see this electron there that jumped? Chlorine ain't never given that electron back. Ever. That's chlorine's electron now. It's got it. It scooped it. It stole it. It's that. And sodium doesn't even want that electron back because sodium is happy now. Look, it's got 8 electrons in its outer shell. Doesn't even want it back. So there is no sharing of that electron. It was taken. It was given. Everything is good. Covalent bonding, not so. Okay? Covalent bonding, this one here is the electrons are not donated or taken or given, so to speak. The electrons are shared. Now, is it 50-50 sharing? It can be. Can it be 75-25? Absolutely. Can it be 90-10? Oh, absolutely. Some atoms are more aggressive than others. Okay? But when you're talking covalent bonding, you're talking sharing. Okay? And you'll see here, this is a water molecule right here, H2O. And you see there we have an oxygen atom. You see it has 2 electrons in its inner shell. Okay, that inner shell is happy. How many electrons does it have here? 1, 2, 3, 4, 5, 6. So it's got 6 electrons in its secondary shell. It's unhappy. It wants 8. Well, here's a hydrogen atom. Okay, you see it's got 1 proton. Hydrogen, there's really not much to a hydrogen atom at all. It's a single proton with a single electron running around it. That's it. So you'll see there's a hydrogen and another hydrogen. And you see its shell, it wants a maximum of 2 electrons, right? Because the inner shell has a maximum of 2. So you see this guy here only has 1 electron, unhappy. And you see what happens here now is these 3 atoms come together and they're all sharing. It's not equal. Oxygen is a very aggressive atom. Okay? It's an unequal sharing of the electrons, but it works. And you'll see there that these electrons are all shared in some capacity. So now oxygen, 1, 2, 3, 4, 5, 6, 7, 8. Happy. This hydrogen here, 1 and 2. It's happy. It's got 2 for itself. And this hydrogen here has 2 electrons. Inner shell has 2. It's happy. And in this way here, we have now formed a molecule. Ionic bonds do not form molecules. They form these crystal lattice, like crystal. Like powders. You look at salt. It's a crystal. All right? That's what ionic bonds form. Okay? Covalent bonds or molecular bonds do not. They form molecules. And you'll see that this is a water molecule. It is its own beast, distinct among the universe. There may be other molecules floating around in your coffee cup, but this one here is its own thing. And it's doing its own thing. All right? And it's not connected per se to anything else. It is a free, that's what molecules are. And you know, the whole idea, you blow onto your hand. You're blowing air and oxygen and carbon dioxide. All these are molecules that are just floating around, okay? They are distinct to themselves. They're not connected. Can they be influenced from other factors? Absolutely. But molecules are individual beasts. The last kind of bonding I want to talk about is hydrogen bonding. Now, and the classic example here is using water, okay? And water is probably 100%, not probably, 100% the strangest molecule in the known universe. It really is. It shouldn't exist as a liquid, but it does. And it's all based on its shape, right? And you'll see there that water molecules, they look like this. Now I'm just going to zoom in here. And you'll see there that there's your oxygen atom, happy, all right? It's negative, right? Because it gained 2 electrons overall, so to speak. So this side of the molecule is negative. These guys here, these 2 hydrogens, they're not as aggressive as the oxygen. So these electrons are going to hang around this side of the molecule. You can see there's no electrons here. So, and what? That's a proton, positive charge. That's a proton, that's a positive charge. So within this individual molecule here, this side is negative, this side is positive. So what you have here is a charge differential. Okay? You have this polarity where one side is negative and one side is positive. And you see how these water molecules are floating around in your coffee cup or a swimming pool. If you ever dived into a swimming pool, you know, and you did a backflip. Okay, we've all done a backflip into the swimming pool, or you did a dive and you did it wrong or something and you landed flat on your back. Right? Water, it's great to have a shower in, I can drink it, but if you flop on your back, water can act like cement. And how does water act like cement? Okay, people have paralyzed themselves by landing flat on the water. And it's for this reason there that water can be like cement. It has this really weird quality to it. We use water there in hydraulics there. You know, the big diggers there at the side of the road doing construction? It's all based on water because you can't compress it. It's so strong. Okay? And it's because of this hydrogen bonding. And you'll see there that for a billionth of a second, as this water molecule comes closer to this water molecule, you'll see there that this oxygen, which is negative, has a billionth of a second attraction to the positive side of this molecule. So there's almost like a zzz, and then this one here is zzz, and then if you have 100 bazillion zzz going on in a swimming pool, that's why there's the great possibility that if you do a bad backflip and land flat on your back, that water, okay, can act like cement and really, really impair you, okay? So this is what we call hydrogen bonding. Another great example of hydrogen bonding is if you turn the tap on just slightly. So you just have a little stream of water, tiny little stream, and then you take a string or a shoelace or something and you hold it up to the faucet. You'll notice that water will actually snake down. There's this attractive quality to the water. Okay, and it's all because of this hydrogen bonding. The water there has a charge. Okay, and we call this polarity. This is what we call a polar molecule. Are all molecules, getting back into where's molecules right here, are all molecules polar? No. Water is a polar molecule where one side of it is negative, the other side is positive. Okay? But not all molecules are polar. Some are non-polar. Okay? Gasoline. Have you ever sat in your car and at a full-serve gas station where some person there is filling up your gas tank? And you know, you're sitting in your driver's seat, and you know, you can see in your side mirror there that the guy is filling up your gas tank. And you ever notice these vapors that, you know, kind of emanate from the gas tank, waviness, you know? Okay? Gasoline is a molecule, bigger molecule than water, but it's still a molecule. And it is a non-polar molecule. And this is the complete opposite of what we're talking about here, where one water molecule is attracted to this one. Okay, so basically all the water molecules in a swimming pool for a billionth of a second are connected. And this is happening a billion times in a second, right? Which is why water can hurt you. Okay? But when you're talking gasoline, it's a non-polar molecule where one molecule has no attraction to the other. So when you open up the gas tank and the guy's putting gas in your car, all of those gasoline molecules are not attracted to each other. So which is why you have these vapors that just emanate from the gas tank, that you can see, which is the whole reason why we should never smoke within 20 to 30 meters of a gas station, because in theory, those vapors can go right to your lighter and go right back into the gas tank and blow up, in theory. Okay, so just to recap, ionic bonding, complete transfer of electron. Okay, the electron never goes back. It creates these crystals. Okay, and remember there that an atom, protons and electrons are the same number. An ion, the protons and the electrons are not the same number, resulting in a charged particle, charged atom, positive and negative. This guy here lost a proton. This guy here lost an electron and became positive. 11 protons, 10 electrons. It has one extra positive charge, so it's positive. This guy here gained an electron. It had 17 protons, has 18 electrons. It has an extra electron. Ion, ion. Cation, anion. Positive, negative. And the last type of bonding there is this is the covalent bonding. This makes molecules where the electrons are shared, okay, in some capacity, creating molecules that can be polar, charge, or non-polar, no charge. And here we've got hydrogen bonding there, where because this is a polar molecule, one side of it is negative, one side of it is positive, that will now create attractive forces within your cup of coffee or swimming pool. So the negative end of one molecule will be briefly attracted to the positive end of another molecule. That's how it works. So ions here, atoms are groups of atoms that carry an electrical charge. There are two types of atoms there. There's what we call a cation, which is a positive charge, and an anion, which is a negatively charged atom. So getting back into here, a positively charged atom, we call this a cation. Okay, ion is any atom with a charge, but a cation is a positive ion. An anion is an ion with a negative charge. Okay. Electrolytes. That's just a fancy word for ions in water. Okay, and that's how your body uses these atoms. It doesn't use the atom per se, protons equals a number of electrons. It uses the ions of those. Okay, so here's the atom, okay, sodium, all right, but this is the chemical symbol. And you're thinking, why sodium? And why do they use Na? Because it's all Latin. And when I was over in Europe there, you can even see there that a lot of countries don't even use the word sodium, okay? They actually use the Latin natrium, okay? So that's why the chemical symbol for sodium is Na, because it's Latin, all right? So we use sodium there for fluid balance, nerve and muscle function, teeth, bone. We use them all for these here. Calcium there's components of bone and teeth, blood clotting, muscle contraction, nervous function. Iron, okay, which comes from the Latin there for ferrous. That's why iron's chemical symbol is Fe. Components of hemoglobin, all right, for oxygen transport. All right, interesting stuff. More of them here, okay. There's your hydrogen, okay, chemical symbol H+, okay, important there for acid-base balance. Its concentration determines the pH of a solution, acidity, right? Potassium, bananas, okay. And the Latin for potassium is kalium with a K. So that's why the chemical symbol for potassium is K. All right. And you see any of these pluses here, cations, these guys here have lost an electron. And you see here calcium lost 2 electrons and became 2 plus. Iron as well lost 2 electrons. So these are cations here there that we use. There's ammonium, which we'll get into further there when we get into renal and kidney. Okay. There are some important anions here. You remember an anion is an atom with a negative charge. And there's your chloride again, Cl-1. Okay. There's also one there called bicarbonate ion. This one here, the body is amazing. This whole idea there that we're blowing out carbon dioxide. Carbon dioxide is a junk product. It's meant for the garbage, and that's why we blow it out. But what the body does is it takes a junk product that's on its way out and changes it into bicarbonate ion just before we exhale it out, so that we are able there to keep our blood buffered. And our blood has to stay at a particular pH, and we'll get into pH there when we're talking about acid-base regulation. Okay, and our blood has to be maintained at a particular pH, okay, or we will die. Okay, we use bicarbonate ion. We'll hit that one there when we get into respiration. Phosphate, PO43 negative here. This is what we call this is a phosphate polyatomic ion. You'll see there's many atoms. There's 5 atoms involved here. By the way, how many atoms do you see in here? Hopefully there you can see 5 in the bicarbonate. There's a hydrogen atom, a carbon atom, and then there's 3 oxygens. Okay, and the phosphate polyatomic here, there's 1 phosphorus and 4 oxygen there, components of bones and teeth there, components of ATP, which we'll get into there next week, as I recall. When we the whole idea there that why do we eat food? For energy. And it all relates back to why exactly do we breathe oxygen? Interesting. We'll get there. So electrolytes and ionization. When an electrolyte breaks apart in solution, the electrolyte is said to dissociate or ionize. So here, remember the example there, putting salt into water, making a salt water solution, right? Take a tablespoon of salt, put it in a glass of water, stir it, and away you go. Well, here's your salt. You put it into water, and what goes on here is the water, oxygen is a very, very aggressive atom. Like if you have a lasagna plate or biryani, you just have a great big party there and you're not doing the dishes tonight. Forget it. So what do you do with that lasagna pan? You fill it with water and let it soak overnight, right? It's the oxygen in the water that goes in and starts attacking the lasagna, or if you put salt into water, it starts attacking that solute there, or it starts attacking. And ultimately, it's what gives us wrinkles and takes us out in the end. So oxygen, we need it to survive, but it also takes us out in the end and makes us old. All right. So oxygen is a very aggressive atom, and you can see there these water molecules. Okay, and here they go in there and they start attacking this salt crystal that you just dissolved, or you put it into your glass, and it starts breaking it up. And you'll see there, chlorine is a negative ion. Well, look how the water molecules are arranged. Remember those hydrogens there? That was positive, 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 is holding the negative ion in place. Sodium atoms, okay, which are positive because they lost an electron, they are being supported by the negative side of the water. There's your oxygen. You remember that those guys are negative. And that's how making a solution works. Okay? Moving on here, we're going to talk about the differences there between a molecule and a compound. We're going to talk about the role of a catalyst and an enzyme. The whole idea there. We're going to differentiate between acids and bases. We're going to look at a little bit of pH. We're going to look at ATP minimally, and mixture solution suspensions in the precipitate, colloidal, all this kind of stuff. Let's go. So, molecules and compounds. So molecules, two or more atoms bonded together. So you have, look here, oxygen. Remember what was the magic number in chemistry? 8. That's right, right? So you look at this oxygen here, it's got 2 electrons in the middle in its first energy, happy. Okay? And then it's got 6 electrons around the outside. It's not happy, it needs 8. And this oxygen, which is the same, it's got 2 and 6, it's not happy. So what happens here, one oxygen atom will bond with another, and we get O2, an oxygen molecule. This is what we're breathing in, people. This is the molecule there that provides us with life. And you'll see there that this oxygen is creating a molecule with this one, and they're sharing the electrons. So you got 1, 2, 3, 4, 5, 6, 7, 8 electrons. So happy. 1, 2, 3, 4, 5, 6, 7, 8. This guy here is happy. So this is what we call an oxygen molecule, and this is how oxygen exists in nature. O2. Hydrogen. It's a smaller one, so you'd look at the inner shell there. It has a maximum of 2. Well, hydrogen only has 1, so one hydrogen mixes with another. Look, they're sharing. This guy has 2. This guy has 2. They are happy. This is how hydrogen exists in nature. And there's your water molecule there. You remember, right? The electrons are going to be hanging around this oxygen more than here. So this side is going to be negative. This side is going to be positive. We have a polar molecule. Have a look here. Who's the big boss here? Well, just looking at it, there is no big boss, right? This oxygen is the same as this oxygen. So these guys here are actually sharing those electrons equally, 50-50. This is a non-polar molecule. No attraction to any other molecule in the known universe. Okay? This guy here is pulling these electrons 50%. This guy here is pulling these. So non-polar. The same thing here. Hydrogen, a non-polar molecule. No attractive forces because this guy is the same as this one, 50-50. And that's why this is a polar molecule, because there is a big boss. And this guy here is going to be dragging those electrons to this side, negative, positive, polarity, non-polar up here. Okay. So molecules, 2 or more atoms there bonded together. A compound, molecules formed by 2 or more different atoms. We'll get more into these as we go. So water, a vital substance, universal solvent. Gets rid of lasagna there the next day. Like, you think about that, right? You fill your lasagna pan up with all those crusty bits there. You fill it up with water and then go to bed. You wake up there the next morning. Clean as a whistle, right? Because the water did all of the work for you. Universal solvent. It will break down anything over time. Temperature regulator. Absolutely. The whole idea of releasing sweat. The sweat is just hot water. And if you get the hot water out of the body temperature cools. Ideal lubricant. Crucial part of most chemical reactions. Okay, solution chemistry, we'll get into that. Crazy important. Protective mechanism. Okay, without water there, it wouldn't be around. So let's get on with things, shall we? Oxygen, carbon dioxide. Important compounds and molecules. So oxygen, O2, which we just saw, is a molecule composed of 2 oxygen atoms and exists in nature as a gas. The air we breathe is about 21% oxygen. Okay? And you think about that, it's just, trees, vegetation, they breathe in carbon dioxide and breathe out oxygen. We breathe in oxygen and breathe out carbon dioxide. It's worked for billions of years. What a beautiful system. I hope it continues for billions of years more. Carbon dioxide is a compound that consists of 1 carbon atom and 2 oxygens. Can you see it? Okay. 1 carbon atom, 2 oxygens. Carbon dioxide. All right. Hopefully there you can see that. I always put a question on there. Can you, how many of each atoms are within a particular molecule? Have a look. So CO2 is a waste product, so it must be eliminated from the body. Chemical reactions, this here when we're talking about the interaction of atoms, okay, and how they come together in a particular reaction. The whole idea there that hydrogen and oxygen can come together to make water. Okay, chemical reaction there. You remember there, what slide is this? 26. Let's go back up, shall we? You remember this whole slide. Can I get my eggs back? Chemical reaction, nada. Okay. Where was it? Right here. So, a catalyst, this is an enzyme, okay? It can be an enzyme. Generally, there are enzymes in the body, but they can be other. There's different kinds of enzymes here. These are chemical substances that speed up the rate of chemical reaction, okay? And our body, we utilize enzymes, okay, in our body to facilitate all of these chemical reactions. A little experiment there. It's kind of gross, but you take a piece of bread, just normal piece of bread, white, brown, whatever, chew it. Don't swallow it for a couple of minutes there. It'll turn. You just keep chewing it and keep going at it. Just don't swallow it there, and it's actually kind of gross. It'll turn into this kind of gelatinous, mucusy, saliva, bready mixture in your mouth, right? But you have enzymes in your mouth. One of them there is called amylase, and what it does is it breaks down starch. And what will happen, you know, after a couple minutes of just kind of chewing on this bready, gelatinous mixture in your mouth, is it will start to turn sweet, because all those enzymes in your mouth are going in, breaking up the starch molecules that compose bread. And if you didn't know it, you know now, starch is just sugar. That's all it is. So we'll get more into these as we go on, but a catalyst is a chemical substance that speeds up the rate of chemical reaction. And that's why our body temperature is such, that's why our body pH is such, because it's all about enzyme regulation. All of these hundreds of bazillions of enzymes that are working in our body at the moment, they need a specific environment to work in. And remember that word, homeostasis? It maintains that specific environment so that these enzymes can function normally. Okay? So an enzyme, a protein that serves as a catalyst. Okay? So just going back into that little experiment, the whole point of that experiment was chewing a piece of bread. Eventually, after a couple minutes, it will start to taste sweet, because bread, carbohydrate, starch, it's just sugar. That's all it is. Acids and bases. An acid is an electrolyte that dissociates and makes hydrogen. Okay? Acid has I shouldn't say too much, but an acid has more hydrogen in it. And what do I mean by that? Like if you think of vinegar or lemon, even yogurt, it's that tang. You know, you sprinkle some lemon onto a salad, it just brings that brightness. That's the hydrogen, that tang. Yogurt has a tang to it because it's slightly acidic. Bases, though, okay, these are substances there that produce hydroxide. Okay, hydroxyl ion right here. This is OH minus. This is the kind of universal symbol there for a base. Now bases, we eat more acids than bases, generally speaking. I guess you can eat a bar of soap. You know, I wouldn't recommend it, but the whole idea there that cleaning products, soap, they tend to be slippery substances. That's one of the definitions there of a base. Okay, and you see there that bases, OH plus the hydrogen makes water. You see that? H2O. So if you add baking soda, which is a base, all right, baking soda is a base. It produces hydroxide ions. And if you mix vinegar, which is an acid, okay, right here, you mix both of these things there together, you get a big reaction. I don't know if you guys have ever done the volcano. You know, you get a bottle, you mix some baking soda inside, you put the sand up, and you put in some vinegar, and all of a sudden, you get a volcano, right? Well, yeah, that's what's going on. You get an acid-base reaction, and you end up making water. That's it. All right. So here we're talking about pH. This is the pH scale. pH just stands for potential for hydrogen. That's all it means. And you'll see there that your pH scale goes from 0 to 14. All right? And neutral is 7. Deionized water, you know, if you buy it from Culligan, you know, those big, you know, blue water jugs there, it'll be the red cap. Okay? Reverse osmosis, where that has nothing in it except water. Pure water has a pH of 7, where the amount of acid equals the amount of base. All right? That's what we mean, pH neutral. That is pH of 7. Okay? Anything less than 7, have a look here at my hydrogen concentration. So anything from 0 to 6.9 is an acidic solution. And you'll see there, in and around 7, my hydrogen equals my hydroxyl concentration. That's why it's neutral. But your pH scale, the lower you get, the hydrogen concentration increases while the OH concentration decreases. So as you get closer to the outside here, like 0 and 1 and 2, the hydrogen concentration is much, 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 much higher. Okay? Like millions and billions of times higher than the base concentration right here. Stomach acid has a pH of 1.8, 1.2. Okay? This stuff dissolves anything. Battery acid from your car has a pH of about 1. Dangerous stuff over here. Dangerous acids. And you look at the amount of acid in comparison to base, dangerous stuff. Okay? Lemons, vinegar has a pH there about 3 and 4. Okay? Coca-Cola has about the same pH as your stomach acid, about 2.3. Yeah, have a glass of Coca-Cola, all right, and put 25 cents in and leave it there for a week. See what happens. Coca-Cola, not good for you. Going on the other side of the scale here, any pH above 7 is what we call basic or alkaline. Okay, and you'll see here it's just the reverse. This is where the hydroxide concentration is much, much higher, okay, than the acidic concentration here. And again, when we're dealing with the ends, these tend to be dangerous. Like I would ask you, which is more dangerous, an acid or a base? Well, they're both dangerous. If you have an acid with a very, very low pH, watch yourself. That thing will eat through a countertop. If you have a base with a very, very high pH, that is also very dangerous. An acid burn looks exactly the same as a base burn. Dangerous, dangerous. It's in this region, though, that we should be okay. Vinegar, milk. Milk has a pH of about 6.5. Milk is slightly acidic, but not dangerous. So in this region here should be okay. There's not a lot of foods there that are basic, so to speak. There's baking soda, all right, these ones here. But just remember there that a basic solution has a high pH, okay? And the more extreme it gets, the more dangerous it gets. An acid will have a low pH, lower than 7. And the closer you get to the extreme, the more dangerous it becomes. Okay? Good. There's the pH scale in a nutshell. Blood pH is right in here. And I'm kind of, it's about 7.35. And yes, you heard me correctly. Blood pH is about 7.35. And if it deviates from that by really any means. Anywhere between 7.3 to 7.4 is acceptable. But anything outside of that range, you're into acidosis or alkalosis, basic. And that's blood poisoning. And it is very, very serious, and you will die if you don't get it fixed. Okay? Moving on. So, reading the pH scale, there's your acidosis. Okay? That's your pathology, your disease there when there's too much hydrogen and the pH is less than 7.35. Like 7.25, man, you better get to the hospital. 7.1, you know, it's very serious, and it doesn't have to deviate much from this set point. Alkalosis, alkalosis there, it's too much hydroxide, not enough acid there, and this is a pH greater than 7.45. So our blood pH does not fluctuate at all, and if it does, it is very serious. 6 forms of energy. There's mechanical, okay? There's chemical. There's electrical energy. There's radiant energy, thermal energy, and nuclear energy. So you see here, what is energy? It's just the ability there to perform work, which is why we eat food. Okay, we break down this food. And just getting into why we breathe oxygen. Hopefully there you had a chance to go camping there this summer, and you had a nice little campfire there, and you throw some logs on the fire. What gas is involved in that log or wood burning? Well, it's oxygen, right? Oxygen feeds fires. Well, you're breathing oxygen. You're burning that breakfast you had. The only difference is there's no fire in your tummy, because that would be counterproductive to living. Our body is there. It's able to capture this fire and store it as energy so that we're able there to do what we need to do. Okay, so you guys can have a look at these there. There's mechanical energy, there's radiant energy, nuclear energy, there's all these different types, and energy can be transformed. Okay, the whole idea there that you put gasoline in your car and then you turn your car on, your car goes. Okay, you've changed chemical energy into mechanical energy, but really the most of the energy there from your car is just dissipated as heat. Same for us. The majority of the energy there that we eat and consume, the majority of it is given off as heat. Okay, our muscles produce the majority of our heat, and that's why we are warm-blooded creatures. Okay. Energy transfer, this one here, ATP, adenosine triphosphate. Because there's 3 of those. Remember those phosphate PO4 molecules there that we saw up top and a couple slides ago? This is our energy currency. This is how we spend our, you eat the banana, you eat your food, the body takes the energy from that food and makes ATP molecules. It's these ATP molecules that the body spends in order to go running or thinking or driving. All the daily activities there that we do, we spend ATP molecules. That is our energy currency. Okay? After the food we eat is broken down, energy is released. The energy is transferred to ATP molecules so that we can now utilize those to do what we need to do. And this is an ATP molecule right here. Those phosphate molecules, PO4, that we saw earlier. Okay, there's a sugar backbone, and then there are bases here. And we'll get more into this as we go. But the whole idea there that when we eat bananas, we eat our food, we make these molecules, and then we are able to spend them to play soccer, go swimming, do what we need to do. Okay? This is our energy currency. So, there we go. We store the energy, and the energy is then released. Okay? And we use those ATP molecules as we need to. Okay? And we're able to do there the things that we want to do. Okay? we're almost at the end here. I know that today was a little long one there. We're into our third hour here. Generally, but we had some introduction there to do and all that kind of stuff. But we're almost done. You guys are doing great. You really are. Mixtures, combination of two or more substances that can be separated by ordinary physical means. So if you mixed sugar and iron, mixture there together, iron pellets with sugar, we can easily separate these two things. And you're thinking, what? Even, iron filings and sand. What are you going to do? You're going to separate them like this? No, you just get a magnet, hover it over your sand iron filing mixture. All the iron will come up onto the magnet, leaving you there with pure sand. Dirty water. That is a mixture. Mud and water. We can purify, we can separate the mud from the water and we can get back. It's a physical. Okay? Remember that physical? We can get our eggs back. Okay? Solutions. This is physical. The whole idea there of putting salt into water. I can get my salt back. I can get my water back. This is a physical means. Okay? So solutions have two parts that remain evenly distributed. The solute is the salt. The solvent is the water. So the solute always goes into the solvent. Got it? Salt, solute, goes into the water, solvent. So, substances present in smaller amounts is the substance being dissolved. Solvent, part of the solution present in greater amounts, it does the dissolving. Okay? Two types of solutions. We've got aqueous solutions and tinctures. Okay? I'm more interested in these ones here, aqueous solutions. Okay? Suspensions and precipitates. A suspension is a mixture with relatively large particles. A colloidal suspension, and when you're thinking a colloid, you're thinking milk. Like milk isn't just, just a solution. It has heavy parts to it, right? Which is why if you add vinegar to milk, okay, that vinegar will start to denature all the proteins there in the milk and all that, and we're able to separate the milk, curds and whey, and we're able to make cheese from it. Okay, so milk is a colloidal suspension. There are these heavy particles that are sitting in it, but they don't come out of solution. Precipitate. This is an interesting word. If I have a solution and another solution, and I mix them together, depending upon the solutions there on the chemical reaction, I might get a solid hunk come out of the solution. And it's just part of the chemical reaction here, but a precipitate is a solid that forms and falls out of a solution during a chemical reaction. Okay? Good words there. And this is where we're at. That is the end of today. Okay? I'm just going to check and see here if we have any questions. But yeah, that is all we've got there for today. I want to thank you guys for showing up. Next week there, as I understand, people are working, one job, 2, 3. It's the craziest times I've ever seen in my entire life. So you are not required to be here at this time. I don't take attendance. You make it, you don't make it. What will happen is every week at this time, we will have a live recording, and I'm recording all this right now. And right now I'm going to post all of this stuff onto YouTube there, and I'll send you guys the links through the announcements, and then you guys will be able to access these videos anytime you want. So like next Wednesday, if you're working and you can't be here, you finish your shift, you come on home, you've read the chapters, you come and watch the video, and you're just caught up. Okay, so what we covered there today was, please have a look at your syllabus. The weekly, weeks 1 to 14, that one sheet there, please print off, put it on a wall somewhere in your own little study area. Please make sure you have a little type of study area that's just yours. Like in my house, I think I have about 3 square feet of my personal space. So you know what I mean, divided there unequally between the wife and the kids. but I have my own little workspace there, and I hope there that you guys do too. So other than that, we've talked about the syllabus. We got the videos here. There's nothing going on there for the first couple weeks. I think our first test will be week 3. Okay, so please make sure there to keep on top of things. Let me know if you guys need anything here. My email address is iancoates@georgiancollege.ca, which is also posted on the syllabus, which is posted in the announcements. If you need to get a hold of me, get a hold of me. But other than that, thank you guys for coming. If you guys need anything, shoot me an email. Have a wonderful week. Take care. Be well. Thanks, guys. I'm going to stop recording now. And